Anna is originally actually from Austria, and this is also where she got her diploma from. And she received her doctorate degree, PhD, at the University of Oxford. And as of now, she is a lecturer in materials chemistry at University College in London. And this is where this creepy mummy thing apparently is sitting. And yeah, Anna is a solid state chemist, and she's an advocate for solid state chemistry in her activities, and we're very happy to have you here. And she is mostly going to talk about X-ray photo electron spectroscopy today. And Anna, please share your screen, and we are very excited for your talk.
Excellent. Thank you very much for the invitation and for having me. It's great to give a talk, although I wish I would actually be where the weather is warmer, as in where you are, rather than in cold London. My fingers are somewhat freezing because the heating isn't on yet. But anyway, that should not stop me. So yeah, again, thanks for the invite. What I'll be talking about today has a lot to do with X-ray spectroscopy. And I'll start off giving you a bit of an idea of what the technique is and why we think it's awesome. But then I'll give you basically three kind of working examples, all in the area of power electronics, and what you can find out about materials, and how maybe this technique could be useful for what you're working on. So when spectroscopists talk about X-ray photoelectron spectroscopy, and particularly in the hard X-ray field, we love to use this rather complicated and sometimes confusing overview. So it's basically trying to give you an idea of all of the degrees of freedom of this technique. And basically what you have is you have a sample in the middle that you want to measure. And already with the sample, you have many different options of the geometry that you put your sample in, the environment. So usually we measure in vacuum, but now we can also measure under ambient conditions or even in liquids. You then have a photon source, and that can be different things. And I'll talk a little bit about which photon sources one can use. And then you have on the other side some way of analyzing your electrons. And nowadays we can distinguish not just the energy that these electrons carry, but also things like their spin and their position across angles. And from that you can extract a whole lot of different types of spectra. Some of you may have seen the things in the bottom right-hand corner, which are ARPAS maps, so angle resolved photo emission. But what I'll do in my talk is I'll give you kind of a flavor of how you can use these different degrees of freedom in this technique to measure some nice things. So within the talk, I'll give a very short introduction to XPS, just for if some of you are not so familiar with the technique. Then I'll focus a bit about on hard X-rays. So HAXPAS, what's the point? Why would we want to use hard X-rays? And then, as I said, there are three stories to showcase what it can do. So the first one is on bulk properties. So looking at structure-electronic structure relationships in wide bandgap materials, and in this case, gallium oxide. The second story is all about metallization layers for power electronics and beyond, looking at diffusion barriers and their role. And last but not least, one example of looking at buried interfaces in device stacks. And the example here will be silicon carbide, silicon dioxide. Now, XPS, where did we start off with and what do we do? So in the most simple picture, as I said already, we just have a sample and we somehow expose the sample to a flux of usually monochromatic X-rays, so X-rays of a very specific energy. And when we do so, then we can excite electrons from within our atoms. And we can excite electrons from the core states, so the core orbitals, to the shallow core states, all the way to the Fermi energy. So the technique is intrinsically pinned to the Fermi energy of the material that you measure, so you can measure any states that are occupied in your material. And then these electrons, they're excited out of your material, out of your atoms, and these then so-called photoelectrons, because they're photoexcited electrons, have a specific kinetic energy, and that's connected to the binding energy they had where they came from. So this gives us some idea of the state of the electron in the atom that it came from. Now, the main important physics behind it is the so-called photoelectric effect. The three guys, I don't think need any introduction. They were basically the three instrumental physicists to come up and measure the first photoelectric effect and then explain it theoretically. And the equation at the bottom is very simple, but it's actually complicated when you start to dig in. But it basically tells you what the relationship is between the X-ray source that use the energy of your photons to the binding energy of the electron within the atom to the kinetic energy of the photoelectron that you measure. There's one other term, which is the work function of the spectrometer, the sample, but basically you can see that there's a very simple direct relationship between the binding energy of an electron in an atom and the kinetic energy after excitation. And that's what we can use to understand things like the chemical state, the electronic structure of matter. Now, one thing that's quite important to define, particularly with someone like me who works with soft and hard X-rays, is what do we mean by that? Now, the definition of spectroscopists of soft and hard is very different to a diffraction person. But for us, just for you, for context, if I talk about soft X-rays, I mean up to about 2 kilo-electron-volts of energy. And if I talk hard X-rays in Haxbus, it's basically from 2 to 12, maybe 15 keV. And then some of you might also be familiar with UPS, which uses not X-rays, but UV light. And that, of course, is in the UV range. And depending on which energy you use, you can access different aspects of your material that I'll explain to you in a little bit. Now, soft X-ray photoelectron spectroscopy, that's the standard technique. This is what we usually just refer to as XPS. And one of the main selling points for XPS in the early days was its surface sensitivity. So Kai Siegban, who you can see here, really developed the spectrometers that we use to do these measurements. And he was quite a good salesman. So on the left-hand side, this is one of his original spectra from the early 1960s. And in the top, you see the spectrum of a gold foil. So with these very sharp gold 4F peaks in the blue box. And then what he did to show how surface sensitive the technique was, he took the gold foil and just put his finger on it and measured again. And this is what you see in the bottom where it says after fingerprint. Basically, you have no more signals from gold at all. So the fingerprint already is thick enough to kind of cover your signal. And what you see are the carbon and oxygen from whatever was on his fingers. And as a side note, you can see some nice silicon peaks, which might indicate that he was quite fond of hand cream, because silicon in a handprint is often from the silicone that's in hand cream formulations. But anyway, so this shows you that this is a very, very surface sensitive technique, which is great if you are interested in the surfaces of materials. So any application areas where the surface really determines the behavior of a material, XPS is your friend. But what we often forget is that actually from the very beginning, Siegban and his group used actually hard X-rays rather than soft X-rays. So what you can see here are the first two reported photoelectron spectra, and they were both recorded with molybdenum K-alpha radiation. So radiation even harder than what we would use nowadays. And these are the first core level spectrum on the left-hand side. And then on the right-hand side, this was the first observation of the chemical shift. And the chemical shift is what is at the core of the technique. And it means that if you change the oxidation state of a material, or if you change the chemical environment of the atom that you're measuring, you see a change in the energy position of your peak. And that's called the chemical shift. So a shift in energy that is induced by a difference in the chemistry, in the local chemical states of your material. And that you can use to then identify the chemistry and the electronic structure also of your material. But so it's just maybe important to remember that hard X-rays are not a new thing. They've been used at the beginning, but I'll tell you in a minute why for several decades no one used them. So why harder X-rays? A lot of the stuff I'm going to show in the next few minutes is from a paper that we recently published. And it gives you a big overview of hard X-ray photoelectron spectroscopy in 2020. It includes things like a large survey of all of the existing hard X-ray beamlines at synchrotrons. So if you want to know more about the technique, I really suggest you have a read there. It gives you an idea of all the different flavors, because I would not have time to cover all of this in the next 40 or so minutes. Before I tell you a bit more about what hard X-ray photoelectron spectroscopy is, or why we want to use hard X-rays rather than soft X-rays, HAXPAS really is used across a lot of different areas. So the plots that you see here, this is from data that you can find also in the review. And you can see that the technique in the left-hand side is very dominated by applied physics, material science, condensed matter. So really the materials aspects are really strongly represented in the publications where this technique is used. And on the right-hand side, what this is showing you is kind of an overview of the different scientific topics that this technique is predominantly used at synchrotrons. So you can again see thin films and devices are a big part, and I'll again show you in a minute why that is, and also energy, materials, environment. And then again, you go into things like strongly correlated systems and so on. Now, why hard X-rays? The main motivation is to get away from the surface sensitivity of XPS. As I showed you with the fingerprint, if a fingerprint is enough to cover the surface of your material so you can't measure XPS of the gold anymore, then that might cause a problem if you're interested in things that are heterostructures, where, for example, like in the bottom left, you have an electrode maybe on top of the oxide layer that you really are interested in, or where you have some surface overlayer that you really want to see through, whatever that might be. And with hard X-rays, you can extend the so-called inelastic mean-free path, so how far your electron can travel before it is inelastically scattered. So basically, whilst the X-rays go in quite deep into your material, the photoelectrons have a very short escape depth. So in the photoelectron intensity plot on the right, you have different X-ray sources. These are your main lab sources. And you can see in pure silicon, for one of the main spectral lines of silicon, you can have a maximum probing depth really of 6 or 7 nanometers only. Whilst if you go to the hard X-rays, you can multiply that significantly and you can look much deeper into matter. You get to tens of nanometers, and those are often the length scales that in electronic devices nowadays you're interested in. So this is why we go from the soft to the hard. The main motivation really is this probing depth. There are some other more niche maybe reasons. So for spectroscopists, we can access different spectral lines, which sometimes can be super helpful. But I think in a general picture, the main reason is this probing depth. And just to already give you a very quick example, this is what we've done on a sol gel based kind of transistor stack. It's pretty simple, just on a silicon wafer, and you have indium oxide between 2 metal electrodes, gold at the top, aluminum at the bottom. And what you can do with hard X-rays, you can measure in one spot and in one measurement without moving the sample, without back preparing, sputtering, chemically removing any layers. You can collect all the spectra you see on the right. So you can go through the gold into your indium, you can even measure different lines into the aluminum electrode all the way to the silicon. And at each point, the information from the binding energy positions of these peaks can tell you what the chemical environment is. So for example, in this case, if you look at the aluminum in the bottom middle, you can see that there are 2 clearly distinct peaks. And that is because the aluminum electrode has an oxide layer, because aluminum is very good at scavenging oxygen, and it will scavenge oxygen from the indium oxide. So HAXPAS can probe all of these different buried layers and give you an idea about the chemistry. And as you can see from the thicknesses I've given here, you can probe all the way into the silicon, so 60, maybe 70 nanometers. Now, there is one downside when you go to hard X-rays. And that downside is that something called the photoionization cross-section decreases. Now, what does that mean? This cross-section is a measure of how many photoelectrons you can expect at a given photon energy from a specific orbital. Now, in the plot, you have the 1 electron cross-sections versus the photon energy. Note that the y-axis is logarithmic. So you have logarithmic drops of the cross-sections with an increase in photon energy. And the colored bars tell you where your soft X-ray range is, and then 2 of the dominant lab sources, chromium and gallium. And you can see that your cross-section, and therefore your signal intensity, drops by orders of magnitude. So this means that in general, for hard X-rays, you need some pretty bright, pretty intense X-ray sources. And that is one of the reasons why hackspace is still predominantly undertaken at synchrotron sources around the world. And on the map, you can see some of the big players. So there are quite a few synchrotrons in the US, but also in Europe. There are a total of 25 beamlines that are running at the moment at 12 synchrotrons. But what is a bit of a caveat, or maybe something interesting to note, is that Spring 8 in Japan has basically half of those beamlines, right? So in essence, there's a clear concentration at Spring 8 in Japan, and then the rest of the world only has half. And if you think about it, I mean, imagine how many diffractometers are out there. It's going to be hundreds of thousands, probably, maybe even millions, but there are only 25 experimental end stations where you can do hackspace. So it's a pretty specialized technique. Just to give you an idea what these beamlines look like. So this is beamline IO9 at Diamond Light Source. I'm showing you this because it's kind of my second home. I'm a visiting scientist at Diamond Light Source, and I spend a lot of time at this beamline. It's a pretty special beamline because it actually has 2 insertion devices rather than 1, and it has 2 separate beamlines, one for soft X-rays, which is the blue one, and one for hard X-rays. You have several different optical elements, and then at the end, all the way on the right, that's where your sample sits, and you can converge both of those beams on a very small tenths of micrometer spot on the sample. So you can measure on the same spot on your sample across a huge energy range that you can tune for your specific question. And you also, what's quite important for us is that you can get constant energy resolution across the entire energy range, which means that you can detect very specific states, maybe well-defined states, with the same accuracy across this energy range. So it's a pretty special machine. To give you an idea what this thing looks like, so the 2 pictures show you the end station. On the right-hand side, this is also Smiling Kern. He's a very talented PhD student in the group, just for kind of scale purposes. So he's standing on the platform here. This thing is very tall. It goes all the way to the leaded ceiling of the end station. One thing that helps to identify these spectrometers is this shiny hemisphere that you can see. And that is the photoelectron analyzer. And your sample sits somewhere behind this hemisphere. You can't really see it, the chamber is hidden behind. And then your X-rays are coming from the left here. So this is the synchrotron is somewhere all the way down the line on the left. But so this is what one of these end stations looks like. Now, what's been quite exciting for the community in the last few years is the development of lab-based systems. So as I said, because we need these very high intensity X-rays, we are often limited to synchrotrons. However, the last maybe 5 years, a couple of commercial systems have come on the market that are using high intensity lab sources. And there are 2 options, chromium at about 6 kV and gallium at 9 kV. I'm just showing you the example here of the gallium system. The reason being is that I've worked with it a lot, and we published one of the first papers on the machine. And it's quite special because it uses a liquid metal jet anode. So instead of a solid metal that you create X-rays from, you have a liquid metal of liquid gallium with a bit of indium mixed in. And you can hit this with a really high energy electron beam to create very bright X-rays. And you can monochromate those X-rays. And in the end, you still have a photon flux that is more than sufficient enough to do hackspace experiments in the lab. And on the right, that's the picture. It's also a little bit more compact. You don't have a synchrotron on the other end. But that's been really exciting for the community because it means we have more opportunities to do these measurements beyond what is available at the 25 or so synchrotron end stations. Now, I won't talk too much about it, but another very interesting development, of course, is the advent of X-ray free electron laser facilities. So they are 4th generation light sources that deliver incredibly intense, very short pulses of light. And the first 2 or 3 studies have now emerged where people have used them also for hackspace. This is a very tricky thing to do for many very technical reasons. But if we can get it to work, this of course would be so exciting, because we can then have the time resolution on a femto, maybe an attosecond scale. And for a device person, those are, you know, electronic timescales. So you can start to really kind of uncover some stuff that we've never been able to measure before. So XFELs are really kind of another really interesting development in terms of the photon sources that we use. So we're moving from the synchrotron to the lab to the XFELs now. And there are more and more different ways of doing Higgs measurements. Okay, so this was kind of the end of the my introduction bit on XPS and Higgs, maybe showing you the opportunities and some challenges that we have with the technique. But now I will give you 3 short examples to show you what you can do with it and what you can learn. And the first example, as I mentioned in the beginning, is gallium oxide. And I will only be able to give you a short idea of what we did. If you want to know more about the work, then I've put the paper citation at the bottom. This was excellent work led by a Italian PhD student called Jack Swallow, who was at the University of Liverpool working with Tim Beale's group. And there was a great number of people on here, from theorists to sample growers to experimentalists, who all had to work together to figure this one out. So why gallium oxide? Gallium oxide is one of the ultra-wide bandgap materials that are kind of hailed to be the next step in the development of power electronics. And beyond gallium oxide, in the same group are things like diamond and cubic boron nitride. The definition of an ultra-wide bandgap material is that it has to have a bandgap wider than gallium nitride, which has a bandgap of 3.4 eV. Now, what's really interesting from a material science point of view is that the figures of merit for device performance scale really non-linearly with increasing bandgap. So a small increase in bandgap can really push the figures of merit further. So engineering the bandgap of these materials is really, really important. Now, one thing that has to be said is these ultra-wide bandgap materials are still quite immature in terms of making whole devices, right, and industrializing those devices. So they are still at the beginning of their development. There's lots of exciting science to be done. There's lots of exciting engineering to be done. And that's why we are still kind of, from a fundamental point of view, really interested. So gallium oxide itself has gone through quite a revival. It was quite a hot thing when everyone was really into their transparent conducting oxides. But now it's kind of going through this revival because of its potential applications in power electronics. From a chemistry perspective, a structural chemistry perspective, it's also interesting because it's one of those oxides that exists in a range of polymorphs. So it exists in different structures that all have the same stoichiometry, but have distinctly different local coordination. And the images that you see here are the structures of alpha, beta, and epsilon gallium oxide. And the simplistic equations that I put at the top here show you what the difference is. So alpha has gallium purely in the octahedral coordination. Beta is a 1-to-1 mix of octahedral and tetrahedral, and epsilon is somewhere in between. It's like a 3-to-1 mixture. So the only thing that's changing between them from a structural perspective is this difference in the local coordination of gallium. The stoichiometry is the same. So what we did in this experiment was we had single crystals and epitaxial thin films of these different polymorphs. And then we did a whole bunch of different X-ray spectroscopy techniques, including soft and hard X-ray photoelectron spectroscopy at beamline IO9, which I showed you a moment ago. And then to back up the experiments, we collaborated with some great theorists who did several different levels of theory to match our experiments and to understand what's going on. Now, the first thing in XPS that you would measure are the so-called core levels. So these are core electrons, core orbitals of your material. And in this case, they are gallium 2p3/2 and oxygen 1s. And you can see these are void type functions. So you get some nice symmetric type peaks. In the plots, you can see both the hard and the soft X-ray data. The soft X-ray data is the dotted kind of, are the dotted lines. And one of the things that you immediately notice is that the soft X-rays have this little bit of a shoulder to the higher binding energy, whilst the hard X-ray data is almost perfectly symmetric. And this is due to this probing depth difference that I was talking about. In the surface sensitive data in soft X-ray photo emission, this little shoulder comes from surface states like surface hydroxyls, absorbed water on the surface of a material, while in the hard X-ray data, you don't really have much of a signal contribution from the surface, so you don't see that, and you see the bulk, which does not have this kind of hydroxylation happening that we see at the surface. So that's already quite nice. Now, what's even nicer is that if you look closely at these spectra, you see, whilst the gallium spectra are kind of similar, there's a little difference in binding energy, but the shape is almost the same. In the oxygen 1s spectra, particularly the epsilon phase is very broad. And this is something that you have to explain somehow, because in the spectra, they don't just change the width randomly if you keep your experimental conditions the same, which was the case here. And together with our theory colleagues, who calculated the different chemical shifts of the different gallium sites in these materials, you can figure out that this change in the line width is due to the change in local coordination environment of your gallium. So as I said, in the polymorphs, you have octahedral and tetrahedral environments. They're all slightly different. And what you see is that in the epsilon, which was the 3:1 ratio, the specific energies of these environments start to spread out and give rise to a broadening of your sample. But the magnitude of the chemical shift is not the same for each spectroscopic line. And you can see with the theory lines in the gallium, they're much closer together. So this also tells you have to be a bit careful with how you design your experiments and what you measure. But if you do it kind of in a well thought through manner, you can pick up on these very subtle differences. And this, you can then start to understand the relationship between the local coordination as crystal structure and the chemistry, and in the next step, also the electronic structure. As a side point, that's the last point on the slide, when we go to hard X-rays and by doing these comparative experiments, we can also exclude a lot of reasons for this line broadening. So we can convince ourselves that this is truly intrinsic to the material and not due to some surface states or some specific microstructure, or maybe some extra transitions, maybe plasmons, etc. So it's really useful to use combinations of soft and hard X-rays. Now, we want to, of course, go beyond saying, oh, well, you know, there's a relationship between coordination environment and chemistry. And we want to unpack what that means for the electronic structure. So what you see here in the middle panel, in panel B, are the valence band spectra. So photoelectron spectroscopy directly probes the valence electrons in your material and the valence bands in a solid. And we have measured this in both the soft and the hard again. And here, what you can see, they look very different, and that's due to these cross sections. I said, you know, the cross sections drop when you go from soft to hard, but also relative to each other, they don't drop at the same rate. And this is what you see here. So you can see this drop here is predominantly due to the difference in cross sections between S and D states going from soft to hard X-rays. And you can compare these experiments, so those are the lines, with the theory, and in this case, density functional theory, which you can see in panel A. These are projected densities of states corrected for the cross-sections of our experiments. And with the help of theory, you can now figure out where in this valence band is what kind of atomic character, right? Where are the gallium states, where are the oxygen states? You can talk about hybridization and also changes in the positions. And now these are very subtle differences, but there are very distinct differences between the polymorphs. You can see changes in the relative positions of these different wiggles, basically in your band, of the different intensities. And that basically is really the minute differences in electronic structure that are caused by this local coordination. And you can show this even further in the right-hand picture. These are now density functional theory calculations where we've projected on the octahedral and tetrahedral gallium sites separately. You can see they're quite different, and then you can basically do a little trick and add them together in the right ratios. And if you compare that to the spectra, you can, for example, explain why this peak in alpha is really strong, because this is your tetrahedral coordination environment. And so with this, you can start to really pick apart your valence electronic structure and understand why maybe one of these polymorphs has higher carrier concentrations or works better in the device. And the next step further then is that you want to not just probe your occupied states, your valence states, but also your unoccupied states, your conduction band. And you can do that by combining photoelectron spectroscopy with X-ray absorption spectroscopy, XAS, because in gallium oxide, the oxygen KH spectra are representative of the unoccupied states of the material. And if you do this carefully, you can put them basically together. So you have your valence band spectra, in this case from the soft X-rays and the DFT on one side, and then you have your XAS with BSE typed theory on the other. And now you can start to talk a little bit about band alignments, changes in band gap, but you can play the same game we've done for the valence bands for the unoccupied states. And again, we can start to figure out with the help of theory what the differences are, what the different contributions are. So for example, these B and C features in the spectra, which change quite significantly, are from oxygen 1s states that are predominantly bonded to tetrahedrally coordinated gallium. So again, you can then really see at what point in your band structure do these coordination environments play an important role. Okay, so this first example gives you an idea for a bulk material, how photoemission and X-ray spectroscopy can help you correlate local structure, changes in local structure with chemical changes and changes in electronic structure, which is quite crucial when you're trying to kind of materials discovery and trying to find new materials for electronic applications. The second example, and this is now Olaf Kern's work, who you've already seen his heroic picture next to the end station at beamline IO9. And this work is on not the semiconductors, not the dielectrics, but it's all about the metallization. And in this case, we were looking at a modern type of metallization, which is the so-called titungsten, so titanium tungsten copper system. Now, within the kind of remit of power electronics, the high power applications put really tremendous, really harsh requirements on the semiconductor and on the dielectric materials. For example, in the silicon carbide oxide that I'll show you in this last example. But they also require these new generations of metallization concepts. And copper is really the industry standard now, but it suffers from one problem, and that is that if you just put copper on silicon dioxide, so put the metallization directly on your dielectric, copper will diffuse into silicon oxide, form copper silicides, and this will lead to device breakdown. So what you need is a diffusion barrier, and titanium tungsten, or titungsten as I will call it, is one of the standard diffusion barriers that is widely used. However, there are some challenges to optimize the composition and the structure of these diffusion barriers. So one thing that we know is very important for these barriers is the ratio of titanium and tungsten to each other. This influences the stability and the efficacy of this titungsten layer as a diffusion barrier for copper. And the way that it's understood that this works for now is that the titanium decorates the tungsten grain boundaries, and that stops the copper from diffusing through the titungsten layer and into the silicon. So you can see in the bottom left-hand schematic, this would be a very simplified device stack. So you have some form of semiconductor like silicon, a dielectric on top, then you have your diffusion barrier, and then you have the metallization on top. In the ideal case, the copper now can't get to your silicon dioxide and device breakdown is averted. However, particularly in power electronic devices, these stacks experience very high thermal loads, so very high temperatures. And that means that the titanium will start to diffuse out of the titungsten layer and into the copper. Now, if this happens too much or too rapidly or at the wrong point in the device operation, the copper then has a way of diffusing through the barrier down, because the barrier starts to degrade, the titanium that's decorated the grain boundaries comes out, the copper can now diffuse down. And if that happens, ultimately, as I said, these copper silicides form, you can have accelerated device failure, delamination, etc., etc. And beyond the titanium tungsten ratio that we know influences at what point this breakdown happens or how stable this diffusion barrier is, we also know that oxygen in trace amounts in the device stack can strongly influence this behavior. And this is where photoemission comes in. So this is quite a complex problem that we're trying to solve here, and I'm only showing you one small aspect of it. But in the whole project, we've used a combination of photoelectron spectroscopy techniques to really pin this thing down. So we used standard surface sensitive photoemission combined with sputtering, Hack-SPAS, resonant photoemission to look at the electronic structure, and even in situ annealing. And I'll just give you a couple of examples that kind of build then up an overall understanding of this material. So on the right-hand side, these are a lot of spectra. I don't expect you to look at all of them, but this is a systematic study in depth across different titanium concentrations to understand this influence of titanium to tungsten ratio, but also the presence of oxygen. And what these lines tell you, if you look at the very top left, for example, this is a tungsten line, you can see that there are at least 3 different oxidation states of tungsten that can emerge. So metallic tungsten, which is what you want, but also oxidized tungsten. And these are not straightforward stories. So you can have partial oxidation. There are equilibria that drive the oxidation back and forth. And depending on which part of these diffusion barriers you look at, going further down with the soft X-rays and then with the hard X-rays, you see basically an evolution of the oxidized states, both in the titanium and the tungsten. And that can help you sort of in depth across the diffusion barrier, can help you understand oxygen distributions, oxidation state distributions, and ultimately help identify why breakdown might happen. Now, this oxygen part is quite important. And what's even better is, instead of just looking at different titanium tungsten ratios, we can also look at this a little bit dynamically. So we can follow the differences in these barriers. And this is just the example of the tungsten states here with thermal loading. So with annealing, which basically is representative of the thermal load during the manufacturing of these semiconductors, but also during operation. And whilst you would always expect that titanium would easily react with oxygen because it's a very good getter. It likes to absorb oxygen a lot. The tungsten, actually, you wouldn't expect to oxidize that much if there's titanium around. But what you can show is that depending on the titanium concentration and on the thermal loads in these devices, by careful peak fit analysis of these core levels, you can show these differences in oxidation states also of tungsten. The tungsten partially oxidizes, and that has a huge influence on this kind of behavior of your titanium tungsten diffusion barrier during operation. Now, you can go beyond just qualitative pictures of these diffusion barriers and in photoemission in general, where we go beyond just saying, oh, look, there are some different chemical states and there's some electronic structure, that's great. You can quantify this. So on the left-hand side, this is a plot from the same work showing you the changes in relative concentrations of the different oxidation states. So it gives you a quantitative picture, but also for the annealing study in this case, and this is what you see on the right-hand side, and I hope you can see the GIF working, we can study things dynamically in situ. So this is an in situ experiment where we take a device stack and we heat it up to 400 degrees Celsius, and we follow over time the diffusion of titanium into copper. And again, during these processes, we can get both the elemental information and the chemical state information as a function of annealing time, temperature, and also what device we're looking at. So this is really exciting, gives you one example of how we can use this technique and combinations of different flavors of this technique, soft, hard X-ray, resonant, in situ, to build up a complete picture of a problem that we're trying to solve in a device context. Okay, the last 5 minutes or so I'll spend on the final example of silicon carbide, and that's really sort of an epitome of Herbert Krömer's famous sentence, the interface is the device, because what I will show you now is basically, if you can't get the interface right, your device is probably going to be quite unhappy. And this is work that's published together with our industry colleagues at CAI and Infineon, and you can find the 2 papers at the bottom that cover this work in detail. Okay, so again, we're talking power electronics. I've already told you kind of what maybe the next generation is with gallium oxide, with boron nitride, etc. But where we are at with industry standard is really silicon carbide. Silicon carbide is replacing silicon in a lot of the applications. And these types of technology are really enabling new energy technologies, move to electric mobility, And they address all of the different needs that we place on these materials, like reducing weight, saving space, etc., conserving power, of course, and being more power efficient, etc. And you can see in this little kind of comic that the application space is really wide, right? Electric vehicles, of course, that's the main one, for sure, big seller, but also renewable energy, wind and solar, but all the way down to your washing machine. It's surprising how much electronics and also power electronics is in your washing machine and your appliances at home. So these devices are used in a really wide range of applications. And the larger band gap of our wide band gap materials basically gives you more flexibility of how you design your devices, what applications are possible, and also how you can improve the device performance and the stability. And one thing in terms of kind of device performance, if you look at this plot, what might be a bit obvious is that a lot of these applications and where they are placed on this power frequency graph, it's really kind of skirting the physical limits of what silicon can do. It really follows this. And that's because we were for a long time kind of capped at the silicon performance. So now the hope is that with things like gallium nitride in the high frequency area and silicon carbide in the high power area, we can go beyond, we can push further, we can also become more stable and efficient. Now, if silicon carbide is great, right, and it's replacing silicon already, well, what's the problem? Well, the problem is the interface. And it's the interface between the silicon carbide, so the semiconductor, and the silicon dioxide, the dielectric on top. That interface has very high defect densities that have a hugely detrimental effect on the device performance. There's a whole range of proposed defects that might happen from the interface. Most of this comes from theory, including silicon oxycarbides, defects on the oxide side, and dangling bonds on the silicon carbide side. Now, if this is such a problem, how can you already buy silicon carbide devices? Well, the reason is that there is a solution, and it's more of an empirical solution, let's say. So it was found by just trying different things out. And the solution is you take your device stack, you stick it in a furnace at temperatures above 1,000 degrees Celsius, you heat it in something containing nitrogen, and somehow magically you fix the defects, which is great. But you probably want to know why, because you probably want to further improve on this initial kind of idea, like, yes, great, heat very hot and with something with nitrogen, but maybe you want to understand why. So this is again where the photo emission comes in. So I don't need to now remind you, right, that Hackspace is great because we can change, we can look deeper, so we can look at the spuried interface, but we can also tune our probing depth by choosing very carefully the excitation energy and also which line we look at. If you remember the photoelectric effect equation, these are all things that are quite important. We can then tune our probing depth. So for a specific device, we can change the probing depth of the X-ray photoelectron spectroscopy setup. And on the left-hand side, you can see a plot of the inelastic mean-free path, so one measure for probing depth, versus the different core levels that you see on the right collected at different energies. So if you look in the spectra, so these are the silicon spectra, different silicon spectra, they all have two principal states, the silicon oxide and the silicon carbide. And you see that if you go higher in energy, higher in kinetic energy of your electron, you see more and more of the carbide and less of the oxide. So this you can now use to build up sort of a non-destructive depth profile. Now, what we were interested in these studies was to figure out what the difference is between different nitrogen atmospheres used in these high temperature anneals. So we have N2, NO, ammonia, and a combination of NO and ammonia. And somehow you can already see, particularly, for example, in the silicon 1s at 6 kilo electron volt, there's stuff going on, right? Our spectra start to move, the widths are starting to change. And as you've seen in the gallium oxide case and in the tungsten case, that means our chemistry is changing. So somehow when you anneal, something in the chemistry is changing. So now the question was, what is it? And to uncover that question, we particularly focused on the nitrogen 1s spectra, because somehow that nitrogen is reacting with our stacks. And what a combination of soft X-rays, which is the plot on the very left, and hard X-rays, which are the next three, is that we can look at the nitrogen across the device stack, so with our different probing depths, and we can start to discriminate between the different chemical states of nitrogen across the device stack, in the oxide, at the interface, in the bulk. And we can, by depth profiling this carefully, you can really pin down where something is. And then at each kind of depth, you can identify your chemical states. And you can see that there's quite a lot happening. The reassuring thing is in N2, which is not reactive, you see nothing, which is always good to have a kind of a null reference. But in all the other three environments, you can see nitrogen species are being incorporated in your device stack. But importantly, they don't react in the same way. You can see different peaks, different intensities, different positions. And if you do this carefully, you can unpack what that means chemically. So one thing that was quite important is that in all the reactive environments, what you can see are these silicon carbon nitrogen environments. And that tells you that somehow nitrogen is able to bind onto silicon carbon dangling bonds, which is one of the main defects that was proposed before, and it can passivate the defect. And by passivating these silicon carbon dangling bonds, it improves the device performance. And the same thing can happen for silicon oxide defects on the other side of the interface. So by combining, again, soft and hard X-rays, by carefully tuning your probing depth, you can probe this buried interface plus the dielectric and semiconductor films and uncover the distribution of defect sites and their passivation in these different environments. So I think this is a really nice example that shows you what you can really do when you start to play around with your excitation energies and have a bit of an understanding of how to tune the experiment to the device stack, to the specific device stack and the specific problem that you're interested in. So with this, I'm done, and I just thought I'd give you an idea of where to next. So we're back to the kind of overview image that I showed you at the beginning. So there are definitely some remaining challenges for the technique. There are still some areas of fundamental understanding in terms of the interaction of hard X-rays with matter that we need to work on. We are working on new strategies to extend our Z microscope, so how well we probe in depth, improving XY resolution. We are for now always sort of limited to the tens of micron scales. And also for some insulators, we might have issues with charging that we're still having to tackle. However, I think that exciting developments outweigh all the challenges, at least in my mind. Particularly now, I think inoperando setups, we're doing a lot more with inoperando electrical biasing, pressure, ambient environments, optical excitations. There's lots going on on the theory side, which is very important for us. And also things like spin detecting analyzers, time resolved studies at XFELS, which I mentioned earlier. So I think there's a lot of exciting developments to come for the technique, but also then for the applications that we look at. And with that, I'm done, and I'd be very happy to answer any questions.
Thank you so much. That was a very nice talk. I always love it because I understand so much more about the technique afterwards, because you have a way to really nicely explain everything. So thank you for that. Are there questions? I don't see anything in the chat yet, but you can just unmute yourself.
Christina, maybe I can start with this question.
Go ahead, of course.
So, yeah, so great explanation, Anna. I also indicated that in the chat box. So I was actually talking to my students about the XPS technique yesterday, and they were quite fascinated because they had a hard time understanding how we can do XRD for the bulk and XPS for the surface characterization. So anyways, I like your description of the diffusion barrier that you talked about. So my question is more coming from the power electronics, because in power electronics, I would assume we have a huge current density that goes into these devices. And once you have such high current stressing in the devices, you're also going to create, you're also going to encounter electromigration. And this can influence the copper diffusion. And in my group, we have been working on electromigration for a while. So how does the presence of diffusion barrier influence electromigration? Is it useful to sort of arrest the motion of copper into the silicon?
Yeah, so the diffusion barriers are not just there for the thermal kind of problems that you might face. But basically, it is a very, very effective diffusion barrier for copper. So it really, because it has no obvious pathway to get through this. So it has a very low diffusion coefficient in tungsten itself. And then by decorating the grain boundaries with the titanium, you really kind of stop it in all the different ways that it might try to migrate through the diffusion barrier. And these diffusion barriers already work, right? So they are implemented in device structures. It's just that if you start to push your device higher, so higher power loads, higher temperatures, at some point you do encounter this device failure. And now the idea is to understand exactly why, and then of course how to improve it. Because one thing that you can play a lot with in these kind of bimetallic systems is this ratio of how much titanium do you put in, and more is not necessarily better, right? So there's clearly a sweet spot where you can then also increase the power load and still don't see this detrimental diffusion.
So is there, like, if I can change I can engineer the defects, for example, if I say prohibit the sites where copper can diffuse, say if I can change the vacancy concentration in the defect barrier, in the diffusion barrier, does that help?
I think there are many different ways, right? So I mean, the example I showed, this titungsten, is also only one example of a diffusion barrier. So I think there are different strategies of how you stop the diffusion, right? Grain boundary decoration is one of them, but also, designing materials with maybe high defect densities that can capture the copper atoms as they go through would definitely be an alternative, right? And there are also other thoughts of like structuring these things, or and of course there's also a thickness dependence. So you did, or multi-layer stacks even, right? There are lots of different ways of doing it. The only thing, you still have to somehow retain your metallization contact, right? Still has to be somehow an electric contact, otherwise it wouldn't work. So
yeah, thank you.
Krishna, yeah, you have a question?
Yeah, so how sensitive is the interface to the underlying fabrication technology? Like, I mean, if it's solution-based versus layer by layer deposition, how sensitive is it?
Yeah, so we look a lot at process control type questions, right? Where we look at the influence of different synthesis approaches, deposition techniques for thin films, but also for other materials, right? I mean, we do this for bulk synthesis, for nanostructures, layered systems, 2D materials. And in most cases, you can draw very clear relationships between the deposition or the synthesis techniques and the chemistry that you see. Right. And that, I mean, there are many different reasons for this, but it's things like hydroxylation behavior, contaminants, right? Even in your vacuum chambers, you never not have a little bit of oxygen floating about. So all of these things, right? And every technique has different caveats, right? And sadly, XPS is rather unforgiving. We're very good at detecting all of the things no one wants to see. So I think this is one of the strengths, but also for me, sometimes the hard one for the sales pitch, because, you know, people give us samples and then we go back and say, yeah, they have the elements you think they do, but there are another 5 that, you know, and then when we say, oh, you know, we found, I don't know, silicon when there shouldn't be any, then sometimes it's like, oh, we've used a Schlenkline and now we know there's vacuum grease, or there might be all of these different things like alumina boats that are shedding, or glassware. So often you can then help to actually improve the deposition techniques, and that's quite rewarding, right?
Cool. Yeah, sorry, Chris.
Truman, you have a question? Please go ahead.
Hi, thank you for the great talk. I had something of a more basic question. I was just wondering, you had mentioned the trend of the electron mean-free escape path with energy, and also the cross-section trend with energy. And I was wondering why those are inverted. So why does the mean-free escape path increase with energy, but the cross-section decrease?
Mm-hmm. So they're actually based on 2 very different phenomena. So the inelastic mean-free path basically solely depends on the kinetic energy of the electron. So if you excite an electron from matter with a higher photon energy, the electron itself will be quicker. Right. Basically, the kinetic energy is higher and it can escape from, basically, if you irradiate your whole sample with X-rays, photoelectrons are created everywhere. The question is, from where in your sample can they get out? And if they have higher kinetic energy, even the ones deeper down can get out. So that's the reason why if you go to higher excitation energies, you have a higher probing depth. The cross-section, that's quite a fundamental process where basically what we are looking at are still transitions, right? It's an electronic transition of an electron bound in an atom to vacuum. And every transition like this is bound by quantum mechanics and statistics. So there's always a probability. With every transition that you look at, there's a certain probability. And in the case of photoionization, this probability of this electron actually making it out and being excited becomes lower and lower. And this has something to do with the matching of the excitation energy and then how likely it is for this electron to actually make it out. This becomes quite complicated, and actually the theory we have to describe these cross sections is still not great. Like we can calculate them, but they're often still quite off because you have to take into account a lot of different things. But yeah, so they are kind of two different aspects that you need to think about. One is the kinetic energy of the electron once it's made it out, and the other one is kind of the probability of it even being excited in the first place.
Okay, that makes a lot of sense. Thank you. I did have another separate question about the gallium oxide example that you gave. You mentioned that the oxygen K transition was sort of indicative of unoccupied states, and I was just wondering why that's the case in that system.
Yeah, so basically it depends on the makeup of your unoccupied states, because you will know that your first unoccupied orbitals have a certain orbital character. And in gallium oxide, the case is that this orbital character happens to be oxygen. So then you can basically look at, in X-ray absorption, these states being populated, and this is a pretty good representation of your unoccupied state. So it just depends on the orbital character, and depending, once you, for example, from DFT, you've understood what atomic character you have in your valence and in your conduction band, you can try and figure out if there is an absorption edge of a specific material that you can look at. And again, it's about transitions. So you want to have some orbital that you know you can excite electrons into that are representative of orbitals of states that are usually unoccupied.
Okay, thank you.
Maybe I can jump in with a quick question. For your multi-layer stacks that you can basically go from like the top to the bottom, I assume the probing depth is regulated by is it the accelerating voltage, or what do you change on the system to tell it, now I want to go this and this deep? And is that, how precise is that? And is that materials dependent? All of a sudden it's 3 questions, but sorry.
Okay, I'll start with the last one. So probing depth is absolutely material dependent.
Yeah.
So it depends on the density of your material, the valence electronic structure, and other aspects. So for every material, so platinum, terrible, absorbs photoelectrons really well. Something that's not that heavy, doesn't have that many valence electrons, much better, right? So you definitely have to think a little bit about your material. This example with the stack I showed, you don't actually change anything. The good thing in photo emission is that the different spectral lines that you have appear at different energies.
Right.
So as long as the lines are not on top of each other, I simply just measure different energy regions at the same energy, and I get all the information of the different layers. In an experiment like the silicon carbide, where we're trying to really hit a specific point or make sure that most of our information is coming from a different depth, there, what you need to change is the kinetic energy of the electron, right? The photoelectron coming out. And the easiest way to do that is by changing your excitation energy. What I didn't touch upon at all today is to improve your depth resolution. What you can also do is change the angle at which you detect your electrons, because the probing depth is not just dependent on the energy, but also the angle. So for the silicon carbide, one thing that we're doing now is that we first kind of approximately tune, so we see the interface, and then around the interface, we split our electrons that come out into kind of angular slices, and then each of these slices starts to resolve around the interface often at sub-nanometer resolution. But you have to be pretty careful at that point. So this is not something that we do every day, but you can get to pretty good kind of set microscopy resolution.
Great, thanks. Maybe one more question that I had about the last project you talked about with the defects, and that, you know, there was some magic going on at elevated temperatures with something with nitrogen. Has anybody tried doing, now that you know what it is, could you go and like design a specific environment that makes this, you know, the best, or maybe under you mentioned you were working on this with a company, so they might also be interested in, you know, maybe lowering the temperature, and maybe if you have a certain nitrogen carrying molecule, it would work at 700 C instead of above 1000, which would save them a lot of money, you know, by not having to go to such high temperature. Is that something that you followed up with?
Yeah, so for this specific case, what happens is, what I'm showing are the first experiments that we've done. We then gave all of our lovely information back to them, and they went like, okay. So now we actually have round 3, I think, of different processes, different molecules, different temperature ramps, etc. There are a lot of kind of, you know, knobs that you can play with to kind of change this. So yeah, so this is definitely not just a, oh yeah, now we know it's kind of different, like this is where we stop. But particularly with the industry stuff, right, we're trying to solve a problem. So it goes back and forth and back and forth. And then you hope to kind of, as you say, design a specific environment, maybe a different process to cut down on energy costs, because you don't want to anneal at above 1000 degrees. It's rather expensive. And for other reasons, also quite tricky with whole devices, right? So yeah, it's exactly that. So trying to, from what we find out, optimizing those processes and ultimately improving also the devices.
Great, thank you.
I did have one last question. Sorry, you're talking about. I'm just wondering, are your techniques, your spatial resolution, is it mostly limited by the optics of your beamline or the actual geometry of your detector?
Optics. It's all about the optics. So if you could make a smaller spot, you could measure that, right? So our analyzers, in most of the experiments that I showed you, are wide angle analyzers. So we just collect whatever comes out from the footprint of the X-rays on your sample, integrated over your probing depth. And right now, one of the major issues with the monochromators that we need to use, etc., is how do you get that spot size smaller and smaller? And there are now developments, particularly with also the next generation of synchrotrons and X-FELs, to go to nano focus beamlines, where then you basically, what you would do in an experiment, if you wanted to be XY resolved, you move your X-ray spot across your sample, and at each point you collect your spectra and you can build up a picture. We can already do the scanning, but for now it's only on a micron scale, right? So the idea is really to try and go to the nano focus beamlines, but that's a development for spectroscopy beamlines that will only really be available when we go to the 4th generation synchrotrons and X-FELs.
Do you think you'll need different set of optics for your soft and hard X-ray modes? So
yeah, we absolutely do.
Things. Yeah, okay.
Yeah, we absolutely do. So this is why the beamline IO9 that I showed, this is why it's 2 beamlines in one. So you need 2 different insertion devices that are optimized for your energy ranges. And then you also need 2 completely different optics. So one reason maybe to explain this 2 kV cutoff that I said, below 2 kV it's soft and above it's hard. That's because traditionally at that point, you need to switch what monochromator design you use, right? So you cannot use the standard grating monochromators in general for hard X-rays. You need to go to silicon single crystal monochromators. Okay. So it's basically, you always need to have 2 different beamlines, or you are limited in the energy range that you can look at.
Okay, thank you.
We have an X-FEL here in the basement now. You know that, right?
I know. I was supposed to visit, and then the pandemic happened.
Yeah.
Terrible. Yes, I really want to go see it.
Krishna, you wanted to say something?
Well, no, not say. What's the cost of? I mean, you said that there are a few where we don't have to rely on the synchrotron, right? And Christina just alluded to it too. What is the cost of, one of a better word, tabletop
Yeah, tabletop may not be, it's still taller than me, and I'm not that short. So I think this is always a question where I say I probably shouldn't give you an answer. You should probably talk to the companies, but it's a medium-sized pot of gold. So I mean, low 7 figures is probably a good ballpark, around £1 million-ish pounds, though I don't know what that's in dollars or any other currency. So that's kind of your ballpark, and it depends really strongly on what you need on the systems. It's not just the X-ray source and the analyzer. It's, do you need to heat, cool, bias, prep your samples, sputter, anneal. You might want to have some lead on it to check surface if you are interested in that. So, you know, there's a wide range of costs, but kind of, you know, $1 million plus minus is probably a kind of a good, just to give you an idea, ballpark figure.
So it's like a TEM, like probably cheaper than
Yeah.
Okay, that's good to know. So have you had any experience using the, sorry guys, the synchrotron facilities in the US, or mostly you do this in Germany? And
yeah, so actually for me, I mean, for now with the Haxbus, I use Diamond a lot, of course, because it's down the road, a lot in Germany and then in Japan. I haven't actually measured too much in the US because one of the NSLS that had a very nice Haxbus end station, they had the upgrade and then the beamline moved, and then I never somehow managed to get there. So it's on my bucket list, you know, measuring at each Haxbus beamline in the world, which, I mean, it's going to take me a while, but yeah. For now, we predominantly work at Diamond and at DESY in Germany and at Spring 8 in Japan. Also, maybe to some extent, DESY, for example, is one of the end stations that have really done a lot of work to enable inoperando biasing, which for us, you know, it's great to study device things like XC2 and kind of doing things, but if you can bias them at the same time that you measure, right, that's really a game changer for us.
okay, cool. Thanks a lot, Anna.
Well, thank you. I think we are just about hitting our time frame, and I don't see any other questions indicated in the chat. I don't hear anybody speaking up at this point. So thank you so much for this great talk and joining us on a cool
Thanks for having me.
London evening.
Yeah.